NASA has designed a small helicopter that traveled to Mars with the Perseverance rover. Flying something on Mars is very, very hard. There's a lot that went into the design of that helicopter. One of the biggest challenges is that the air density on Mars is very low. So if you wanted to find an equivalent, it would be like trying to fly something at 100,000 feet above sea level on Earth. And we can't even get conventional airplanes to fly there regularly. They can barely even get helicopters to work on Mount Everest, and that's only at a little under 30,000 feet rather than 100,000 feet. Creating lift from the rotor depends on how fast it spins and the density of the air. When the rotor spins, it pushes air downward by the shape of the rotor. And that air pushing downward creates a reaction force that lifts the helicopter up. And when you have less density, you're pushing down less air, so you get less force back out of it. And the only way to make up for that is to push it down faster. Where my research comes in is a quantity that is known as the Reynolds number. And Reynolds number is the major parameter that tells us whether the flow is going to be laminar, which is when it's smooth and orderly flow, or whether it's going to be turbulent going over the rotor. That'd be rough, choppy, chaotic, unsteady flow. And we know what to do with that, but when you're at the scale of Ingenuity, you need to be able to accurately predict where the switch from laminar flow to turbulent flow happens. We call that boundary layer transition. And where that point occurs has a huge effect on the amount of lift you can generate. I had seen NASA using the model that I created, started seeing the same plots from their papers that I knew were created with my model. It was rewarding to know that what I've published, what I've worked on over the past really decade is making a difference and is being used for something that actually flies on Mars.